the perspective that was given us by Antarctica allows us to look at the temperatures in the Arctic and to see that while it's unlikely that there will be a reproducible ozone hole every year, such as occurs in Antarctica, the temperatures nevertheless are low enough to cause type 1 PSCs, which are nitric acid trihydrate, and in some winters are cold enough to reach saturation over ice. In other words, it's possible to dehydrate the Arctic stratosphere in some winters. Well, that perspective was very valuable when results came out from the Ozone Trends Panel, who examined ground-based and satellite data on ozone and found that there was indeed a trend in ozone in the Northern Hemisphere. The trend was in the sense of it being a decrease. However, somewhat surprisingly, the decrease, which measures about 5, 6, 7% over a decade, occurred in January and February, and it occurred at high latitudes around the edge of the polar vortex. Now that's contrary to theoretical prediction, but seen in the context of the Antarctic results was very suggestive. There's the possibility that the Arctic vortex is doing some chemical processing similar to what occurs in Antarctica, but it's not as confined and it's not so large in magnitude, but nevertheless the possibility is that it's causing this ozone reduction.
Too warm?
Yes, it is.
Way too warm?
You're going to actually see the sunrise as you fly west.
Okay.
And then when you get out to Iceland, the solar zenith angle suddenly begins to rise as you turn and come back. And you then capture solar zenith angles down to 82.
Well, that would be beautiful.
It would be beautiful.
There are two things that are essential to ozone depletion in Antarctica. One is cold temperatures and the other is sunlight. It's very cold in Antarctica during the winter, but there isn't any sunlight there. And we don't see ozone depletion happening in the Antarctic during the winter. We only see it during the spring when the sunlight returns to the polar regions. So in the spring, it stays extremely cold in Antarctica, and there's also a lot of sunlight available to drive the chemistry. In the Arctic, during particularly cold years, the wintertime temperatures can approach those of the Antarctic during the winter, but there isn't any sunlight available. As you get into the spring in the Arctic, you get the sunlight, but the temperatures warm up sooner than they do in Antarctica. So you just don't get the right combination of sunlight and cold temperatures in the Arctic. That's the case for the present atmosphere.
However, for research purposes, we have this forecast of the potential vorticity structure at 400 degrees potential temperature. And Norway is here, Stavanger is here, and this shaded contour roughly marks the edge of the vortex. And this region, this shaded region in here is not the same as that. This is a level of shading which shows the edge of the vortex on a much higher potential temperature surface. And this can only be air that has descended diabatically, and as such it's of great interest to us, and we fully intend to fly the R2 through that.
NO values have been running very close to zero for a lot of the time that we've been flying because there hasn't been much daylight. Even now, when there's some daylight, the sun angles are very, very low. With respect to the aircraft or the Earth, they're only on the order of a couple of degrees.
Under this cover is my inlet system. Through 2 holes in the window, the inlet lines come inside. They are all Teflon to guarantee the integrity of the sample. They are heated so that no nitric acid is lost on the inside. On these measurements we have made through the last 4 weeks, we have seen several instances when associated with ice clouds, nitrogen was associated in particles.
Basically, what the ER2 would be seeing if you were flying at 50 kilometers.
Yeah. Okay, this is an abnormality right here. This spot in the spot afterwards is caused by a very high concentrated PSC located right in this region. Very, very high backscattering and depolarization. And it gives us an artifact in the ozone measurement right in here.
Get on with the debrief here. In general, there were, I think, probably more of the PSCs, both type 1 and type 2. They were generally north of 64 degrees. They were very prevalent to the east, large numbers of type 2s. And I think we may be able to have some pictures of that here. You can see these right here. This was on the west side of the aircraft as I was rolling along there. It was a large cloud, certainly a type 2. Looked like it was about maybe 75 to 100 miles long, maybe 50 miles wide. The type 1s are the same as what we saw in the past. Almost identical, Adrian, to what I saw the first flight I had over Antarctica.
5 times 10 to the 14. When we got to here, which is about where we think we crossed the boundary, the HF makes a jump. It's almost a step function and goes up to values of almost 1 times 10 to the 15. At the same time, the HCl is going along, and once we get into the vortex, begins to drop significantly. The LIDARs saw the ozone change somewhere around in here, indicating the boundary.
But the real changes seem to occur over here after we get on the sun run over at about 0. We see a rather large change in ozone dropping. Okay, the peak value is dropping in altitude on down to the 14 range. Okay, being fairly uniform then all the way through the rest of the mission over to Iceland and all the way back to almost into Stavanger.
A big question is what's going to happen as the atmosphere changes. We're changing the atmosphere in a lot of ways. One of the things we're doing is putting chlorine into it, and in 50 to 100 years from now, even if the Montreal Protocol goes into effect, we're going to have about twice as much chlorine in the atmosphere as we have today. And one wonders whether or not that means that the chemistry that takes place in the spring could happen maybe even earlier to some extent. It maybe could happen to some extent in the winter if you had enough chlorine. Another thing that's very important is that we're adding carbon dioxide to the atmosphere. Carbon dioxide at ground level produces the greenhouse effect, which warms things up. But in the stratosphere, carbon dioxide actually cools the atmosphere. And what that means, nobody knows. The big question is whether increased levels of carbon dioxide could lead the stratosphere in the Arctic to behave more like the stratosphere in the Antarctic, to allow temperatures to stay cold long enough for sunlight to be there. There's other things that could also change the temperatures in the stratosphere and how they relate to the sunlight, but it's really that essential combination of temperature and sunlight that controls the ozone depletion.